In this presentation, we propose an adaptive control architecture to mitigate the effect of sensor uncertainties in network multi-agent systems. A multi-agent system consists of multiple agents which can communicate with each other to accomplish a certain task. We can observe multi-agent system in both natural and man-made systems. An example for a natural system can be flocking of birds, schooling of fish, and for man-made systems, we can give an example such as formation flying and network UAVs. We can also divide the problem formulation in multi-agent system in different categories, such as consensus, formation, coverage, flocking or swarming, social networks, and distributed estimations. These are the main categories. There are some other categories, but these are the main. The advantage of using multi-agent system over a single agent system is that in multi-agent system, it uses a decentralized control architecture, and therefore a multi-agent system can distribute computational resources and capabilities across a network. And by doing this, it can enhance the overall system performance in terms of reliability, robustness, and flexibility. So in multi-agent systems, we have two main sections. One is information exchange, and the other one is system computation. And since in a wide range of these systems we have open communication and computation platforms, they are naturally vulnerable to sensor uncertainties and also cyber attacks. We can consider this problem as a classical estimation and control problem, but by doing so, it can only cover the case where we have just a fluctuation about the true value. But in the sensor uncertainty problem, we have measurement devices that are hijacked to degrade the performance. So this problem cannot be addressed using the classical estimation approach. And therefore, for sensor uncertainty problem, we don't know the behavior of the attacker. So we will use adaptive control in order to compensate the effect of sensor uncertainties. Agents in multi-agent systems usually use sensors to measure their state. And like these two guys on the figure, they are arguing about what they are observing, sensors can also be subject to uncertainties. And these uncertainties can be caused by several factors, such as low sensor quality, sensor failure, sensor bias, and some environmental conditions. As we discussed before, the key feature of multi-agent systems is the information exchange. This information can get corrupted by sensor uncertainties or by cyber attacks. So if we have two agents, I and J, if agent I sends Xi to agent J, it can be corrupted by a signal such as delta I. And it can be a time-varying attack or a constant attack. We can consider several approaches for sensor uncertainty problems. The first one is classical fault detection, isolation, and recovery. In this method, sensor measurements are compared with an analytical model of the dynamical system, and by analyzing the residual signal we can determine if a fault has been occurred or not. In practice, it is difficult to identify a single residual signal per failure mode. And also, there is a common assumption in this method, which is all dynamical system signals remain bounded during the fault detection process, which is not a valid assumption, especially if we have some attacks that are state dependent. There is another approach, which is packet losses or disturbances in communication. In this approach, communication links are subjected to disturbances, which correspond to packet losses. And the disturbance model is assumed to follow a particular stochastic process. This model does not necessarily capture the behavior of an attacker. So, in order to address the sensor uncertainty problem, we will utilize adaptive control architecture to be able to compensate the effect of time invariant and time varying sensor uncertainties. Why are we using adaptive control? Because in fixed gain controllers, there's always trade-off between the performance and the uncertainty. These controllers cannot improve themselves, and also they are tuned to a worst case condition, and they assume that the future will be much like the present. And also, fixed gain controllers do not take into account environmental changes in dynamics, and structural damages. And as you can see from the figure, for a fixed gain controller, in order to improve the performance, we need an accurate model. On the other hand, adaptive controllers, they can tune themselves to achieve a given performance, and they do not rely much on the modeling. They can improve themselves under some adverse conditions, and they are not just tuned to the worst case conditions. And as you can see from this figure, for a given modeling accuracy, adaptive controllers can achieve much higher performance than fixed gain controllers. So we are going to introduce a problem formulation. We assume we have multiple agents, xi. They have this dynamic xi dot equal to axi plus bui, and there's two layer. We have an agent layer, which is a physical layer, and we have another layer which is a control layer. We assume that x0 is the leader, that we want all of the agents to follow this one. So x0 is in the control layer, which is a virtual one. And we have some communication links. Here, dashed lines are the communication links which are subjected to a sensor uncertainty delta I. As you can see, we only have access to xi tilde instead of xi, which is a corrupted signal. So in order to design a controller which can converge all of the agents to follow the leader, if we do not have any uncertainty in the system, if delta I is 0, then we simply can introduce the first expression for ui using the true value of xi and xj in order to achieve the following of the leader. But the case that we are considering that we have sensor uncertainties. So delta I is not 0. For this case, we only can use xi tilde in the controller, which is the corrupted signal. And at the end, we added a signal vi in order to compensate the effect of this sensor uncertainty. Vi is called the corrective signal. And we consider two cases here: delta, a constant sensor uncertainty delta, and a time varying one, that is delta of t. For the first case, for time invariant sensor uncertainties, we have just a constant delta. We propose this corrective signal in the blue box vi using estimation of delta, which is shown by delta I hat, and also we have two update laws, delta I hat dot and x I hat dot, in the red box. And in these update laws, we have P matrix. It is we can obtain P by solving the LMI shown below that red box, and in order to avoid some complex computation, we use K matrix as inverse of Q matrix multiplied by Q transpose P. This will convert our LMI to a simpler one, and by picking the value for C such that we can achieve the green box, we can solve for P. This LMI can be solved easily using some toolbox, and after solving for P, we can plug this in into the update laws, and we can obtain the corrective signal VI. So if we define the error signal EI like xi tilde minus x hat minus delta hat, and the estimation error which is delta I tilde equal to delta I minus delta I hat, we can obtain the closed loop system dynamics as it's shown in the green box. Now, by using Lyapunov stability and using this Lyapunov candidate function, we can achieve Lyapunov stability because v dot is less than or equal to 0. And because v double dot is a bounded term, we can use Bauer's lemma in order to conclude that E and delta tilde will converge to 0 eventually. And x tilde, x hat, all of them are bounded, and therefore all the signals that are used in the corrective signal and also in the update laws, all of them are bounded. Now we move on to the second case, which is a time varying sensor uncertainties. For this case, we assume that there is an upper bound for the sensor uncertainty signal delta and also for its derivative. And we propose a similar corrective signal VI and also similar terms for the update laws, but we are using projection operator here in order to guarantee that our update signals are all bounded. By using these update laws, we obtain the closed loop system like this green box here, and we have defined delta P hat and delta P hat on the right. Now, by using the same Lyapunov function candidate, we obtain uniform ultimate boundedness for the signals E and delta tilde, and the bound is shown in the green box here. Again, we can say that all of the signals that are used in the controller in the corrective signal, all of them are bounded using this analysis. Now we introduce two illustrative examples. In the first one, we consider a time invariant case, and in the second one, we consider a time varying case. So we have a system consists of 4 agents in the agent layer, and we have a leader x0 in the control layer. And we have these dynamics for the agents and the leader. So this is the system performance for the case that we do not have any sensor uncertainties. As you can see, all of the agents can follow the leader that is shown by the blue line, and we use the K matrix as this term here. Now we add a sensor uncertainty delta, which are constant values like delta 1, delta 2, delta 3, and delta 4, as shown here. And the performance of the nominal controller are shown here. As you can see, the agents cannot follow the leader very well, and they are diverging from each other. So we need to compensate this effect using our proposed controller. So if we apply our proposed adaptive control architecture for this constant case, constant sensor uncertainty, we can achieve asymptotic tracking for the agent. And on the right, you can see the trajectory of each agent. They can track the leader very well. On the left, you can see the estimation of the sensor uncertainties. And on the right, you can see the error signal, which eventually converges to 0. Now, for the time varying case, for time varying sensor uncertainties, we consider these for delta i's using sign function. In these two figures, you can see the nominal control performance under these sensor uncertainties. As you can see, the agents cannot follow the leader, and they are diverging from each other. Now, if we use our adaptive control architecture, as you can see from the figures, we can achieve uniform boundedness of the signals, and the agents can stay close to the leader. On the left, you can see the estimation of sensor uncertainties, and on the right, you can see the error signal, which is bounded. So, in conclusion, we considered a multi-agent system, and because information exchange is a key point in multi-agent system, we consider the case that we have sensor uncertainties or cyber attacks. The proposed controller can achieve asymptotic stability for time invariant sensor uncertainties, and for time varying sensor uncertainties, we can achieve uniform ultimate boundedness. For the future research, we will consider output feedback adaptive control, generalization to nonlinear dynamical system, simultaneous actuator and sensor attacks, and also time varying communication graph topologies.